Alright, hello everyone, welcome back. I'm your friend in Saxo. Today, we're going to learn a new section.
Conic sections.
Conic sections.
So if we tilt the planes, let me in another color. So an ellipse could be like.
It seems like for some reason, we cannot use a YouTube player anymore. I don't know why, but their own player it's quite bad. I think the user experience for his own video player is not that good at all.
Let's see if we can learn a thing or two about conic sections. So first of all, what are they and why are they called conic sections? Actually, you probably recognize a few of them already, and I'll write them out. They're the circle, the ellipse, the parabola, and the hyperbola, hyperbola. That's a P, hyperbola. And you know what these are already. And I mean, when I first learned conic sections, I was like, oh, I know what a circle is, I know what a parabola is, and I even know a little bit about ellipses and hyperbolas. Why on earth are they called conic sections? So to put things simply, because they're the intersection of a plane and a cone, and I'll draw you that in a second, but just before I do that, it probably makes sense to just draw them by themselves, and I'll switch colors. Circle, we all know what that is. Let me see if I can pick a thicker line for my circles. So a circle looks something like that. It's all the points that are equidistant from some center. And that distance that they all are, that's the radius, right? So if this is r, and this is the center, the circle is the point, all of the points that are exactly r away from this center. And we learned that early in our educations, what a circle is. It makes the world go round, literally. Ellipse, in layman's terms, is kind of a squished circle. It could look something like this. Could look like, let me do an ellipse in another color. So an ellipse could be like that, could be like that. And it's harder to draw using the tool I'm drawing, but they could also be tilted and rotated around. But this is the general sense. And actually, circles are a special case of an ellipse. It's an ellipse where it's not stretched in one dimension more than the other. It's kind of perfectly symmetric in every way. Parabola, you've learned that if you've taken algebra 2, and you probably have if you care about conic sections. But a parabola, let me draw lines here so you know what we're to separate things. A parabola looks something like this, kind of a U shape, and the classic parabola. I won't go into the equations right now, but the classic, well, I will, because you're probably familiar with it. It's y is equal to x squared, and then it could be, you could shift it around, and I mean you could even have a parabola that goes like this. That would be x is equal to y squared. You could also rotate these things around, but I think you know the general shape of a parabola. We'll talk more about how do you graph it, or how do you know what the interesting points on a parabola actually are. And then the last one, you might have seen this before, is a hyperbola. It almost looks like two parabolas, but not quite, because the curves they look a little less U-ish and a little more open, but I'll explain what I mean by that. So a hyperbola usually looks something like this. So if these are the axes, and then if I were to draw, let me draw some asymptotes. I want to go right through. That's pretty good. These are asymptotes. Those aren't the actual hyperbola. But a hyperbola would look something like this. It could either be it would be like, they could be like right here, and they get really close. They get closer and closer to those blue lines, like that. And it happened on this side too. So it kind of, the graphs show up here, and then they pop over and they show up there. So that would be, this magenta could be one hyperbola. I haven't done true justice to it. Or another hyperbola could be on kind of you could kind of call it a vertical hyperbola, and that's not the exact word, but it would look something like that, where it's below the asymptote here, it's above the asymptote there. So this blue one would be one hyperbola, and then the magenta one would be a different hyperbola. So those are the different graphs. So then, the one thing that I'm sure you're asking is, why are they called conic sections? Why are they not called bolas or variations of circles or whatever? And in fact, what's even the relationship? It's pretty clear that circles and ellipses are somehow related, that an ellipse is just a squished circle. And maybe it even seems that parabolas and hyperbolas are somewhat related. This is a P once again. They both have bola in their name, and they both kind of look like opened U's, although a hyperbola has two of these going in kind of opening in different directions, but they look related. But what is the connection behind all of these? And that's frankly where the word conic comes from. So let me see if I can draw a three-dimensional cone. So if this is a cone, let me see. So that's the top. Let me draw, I could have used an ellipse for the top. looks like that. And it's actually, it has no top. It would actually keep going on forever in that direction. I'm just kind of slicing it so you see that it's a cone. And this could be the bottom part of it. So let's take different intersections of a plane with this cone and see if we can at least generate the different shapes that we talked about just now. So if we have a plane that goes directly, I guess if you call this the axis of this three-dimensional cone, so this is the axis. So if we have a plane that's exactly perpendicular to that axis, so let's see if I can draw it in 3 dimensions. So the plane would look something like this. So it would have a line. This is the front line that's closer to you. And then they'll have another line back here. That's close enough. And of course, these are infinite planes. It goes off in every direction. But I'm just trying to. So if this plane is directly perpendicular to the axis of so this is where the plane goes behind it. The intersection of this plane and this cone is going to look like this. And we're looking at it from an angle. But if you were to look at straight down, if you were sitting here and you were to look at this plane, if you were to look at it right above, if I were to just flip this over like this, so we're looking straight down on this plane, that intersection would be a circle. Now, if we take the plane and we tilt it down a little bit, so if instead of that, we have a situation like this. Let me see if I can do it justice. We have a situation where it's, the side, whoops. Let me undo that. Edit, undo. Where it's like this. It has another side like this. And then I connect them. So that's the plane. Now the intersection of this plane, which is now not orthogonal, or it's not perpendicular to the axis of this three-dimensional cone. If you take the intersection of that plane and that cone, and in future videos, you don't do this in your Algebra 2 class, but eventually we'll kind of do the three-dimensional intersection and prove that this is definitely the case. And you definitely do get the equations, which I'll show you in the not too far future. This intersection would look something like this. I think you can visualize it right now. It would look something like this, right? And if you were to look straight down on this plane, if you were to look right above the plane, this would look something, this figure I just drew in purple would look something like this. Oh, I didn't draw it that well. It would be an ellipse. You know what an ellipse looks like. And if I tilted it the other way, the ellipse would squeeze the other way. But that just gives you a general sense of why both of these are conic sections. Now, something very interesting, if we keep tilting this plane. So if we tilt the plane, so let's say we're pivoting around that point. So now my plane, let me see if I can do this. It's a good exercise in three-dimensional drawing. Let's say it looks something like this. I want to go through that point. Oh. So this is my three-dimensional plane. And I'm drawing it in such a way that it only intersects this bottom cone. And the surface of the plane is parallel to the side of this top cone. In this case, the intersection of the plane and the cone is going to intersect right at that point. You can almost view that I'm pivoting around this point, and the intersection of this point and the plane and the cone. Well, this now the intersection would look something like this. It would look like that, and it would keep going down. So if I were to draw it, it would look like this. If I was right above the plane, if I were to just draw the plane. And there you get your parabola. So that's interesting. If you keep kind of tilting, if you start with a circle, tilt a little bit, you get an ellipse, you get kind of a more and more skewed ellipse, more and more skewed ellipse. And at some point, the ellipse keeps getting more and more skewed like that. At some kind of pops right when you become exactly parallel to the side of this top cone. And I'm doing it all very inexact right now, but I think I want to give you the intuition. It pops and it turns into a parabola. So you can kind of view a parabola. There is this relationship. It's kind of, the parabola is what happens when one side of an ellipse pops open and you get this parabola. And then if you keep tilting this plane, I'll do it in another color, so it intersects both sides of the cone. So let me see if I could draw that. So if this is my new plane. Whoops, that's good enough. So if my plane looks like this, I know it's very hard to read now. And you wanted the intersection of this plane, this green plane in the cone. I should probably redraw it all, but hopefully you're not getting overwhelmingly confused. The intersection would look like this. It would intersect the bottom cone there, and it would intersect the top cone over there. And then you would have something like this. This would be the intersection of the plane and the bottom cone. And then up here would be the intersection of the plane and the top cone. Remember, this plane goes off in every direction infinitely. So that's just a general sense of what the conic sections are and why, frankly, they're called conic sections. And let me know if this got confusing, because maybe I'll do another video where I'll redraw it a little bit cleaner. Or maybe I can find some kind of neat 3D application that can do it better than I can do it. but this is kind of just the reason why they are conic sections and why they really are related to each other. And we'll do that in a little more depth mathematically in a few videos. But in the next video, now that you know what they are and why they're all called conic sections, I'll actually talk about the formulas about these and how do you recognize the formulas, and given a formula, how do you actually plot the graphs of these conic sections. See you in the next video.
Right. You know what I was thinking about? I was thinking that compared to all those stupid idea, or let's say concepts, what you most need to know is, or need to remember, is the English word and its corresponding shape or its corresponding graph. That's what you need to remember. For example, a circle is a graph that looks like this, and the ellipse, the graph represent what kind of graph that could represent the word ellipse? It's a shape like this, the pink one. And also, what is a parabola or parabola? I don't know how they call it. I just forgot about that. But you have to know that its corresponding shape or graph is something like this, the blue line. And the last one is a hyperbola. It's where the where the line. Anyway, it looks like this one, the red corner.
In the last video, we learned a little bit about the circle, and the circle is really just a special case of an ellipse. And it's a special case because in a circle, you're always an equal distance away from the center of the circle, while in an ellipse, the distance from the center of the circle is always changing. And you know what an ellipse looks like. I showed you that in the first video. It looks something like that. When I mean that the radius or the distance from the center is always changing, let me say this is centered at the origin. So that's the origin right there. You see here, if we're on this point on the ellipse, we're really close to the origin. This is actually the closest we'll ever get, just as close as we'll get down here. And when we're out here, we're really far away from the origin, and that's about as far as we're going to get right there. So a circle is a special case of this because in a circle's case, the furthest we get from the origin is the same distance as the closest we get. Or in other words, we are always the exact same distance away from the origin. Well, with that said, let's actually go a little bit into the math. So the general or the standard form for an ellipse centered at the origin is x squared over a squared plus y squared over b squared is equal to 1. Where a and b are just any two numbers. I mean, I could have written this as c squared and d squared. I mean, they're just placeholders. But just to give you an idea of what this means, if this was our ellipse in question right now, a is the length of the radius in the x direction. Remember, we have a squared down here, so if you take the square root of whatever's in the denominator, a is the x radius. So this distance in our little chart right here, in our little graph here, that distance is a, or that this point right here, since we're centered at the origin, will be the point x is equal to a, y is equal to 0. And of course, this point right here, this will be a. This distance is also a, so this would be the point minus a, comma 0. And then the radius in the y direction would be this radius right here, and this is b. So this point would be x is equal to 0, y is equal to b. Likewise, this point right here would be x is equal to 0, y is equal to minus b. And the way I drew this, we have kind of a short and fat ellipse. You can also have kind of a tall and skinny ellipse. But in the short and fat ellipse, the direction that you're short in, that's called your minor axis. And so b, I always forget the exact terminology, but b you call it your semi, or the length of your semi-minor axis. Why is it? So let me write that. Semi-minor axis. And where did that word come from? Well, if this whole thing is your minor axis, or maybe you could call it your minor diameter. If this whole thing is your minor diameter, and it's called minor because it's the shortest of all of the diameters of this ellipse, and then the semi is half of that, right? Semi, just for half. So this is the length, b is the length of the semi-minor axis. Semi-minor axis. That's b in this example, just because as I drew this ellipse, it just happens to be that b is smaller than a. If b was larger than a, I would have a tall and skinny ellipse. Let me actually draw one. It could have been like this, right? I could have an ellipse that looks something like that, in which case all of a sudden b would be the semi-major axis because the b would be greater than a, that this would be taller than it is wide. But let me not confuse the graph too much. And in this case, a is the length of the, I think you've guessed it, a is the length of the semi-major axis. Or you could even call it the length of the major radius. I think that makes more sense. Major radius. Major radius. And you could call this the minor radius. I don't like that color. Minor radius. Minor radius. So let's just do an example. And I think when I did an example with actual numbers, it'll make it all a little bit clearer. So let's say I were to show up at your door with the following. If I were to say x squared over 9 plus y squared over 25 is equal to 1. So what is your radius in the x direction? Well, your radius in the x, this is your radius in the x direction squared. So your radius in the x direction, if we just map it, we would say that a is equal to 3, because this is a squared. And if we were to just map it, we say this is b squared, then this tells us that b is equal to 5. So if we wanted to graph this, and once again, this is centered at the origin. Let me draw the ellipse first. So first of all, we have our radius in the y direction is larger than our radius in the x direction. So it's going to, the ellipse is going to be taller and skinnier. It's going to look something like that. Draw some axes. So that could be your x-axis, could be your y-axis. So this distance, this is your your radius in the y direction. So this distance right here is going to be 5, and so will this distance. And this is your radius in the x direction. So this will be 3, and this will be 3. That's it. You have now plotted this ellipse. Nothing too fancy about it. And actually, just to kind of hit the point home that the circle is a special case of an ellipse, we learned in the last video that the equation of a circle is x squared, and a circle centered at the radius, centered at the origin, x squared plus y squared is equal to r squared. So if we were to divide both sides of this by r squared, we would get, and this is just a little algebraic manipulation, we would get x squared over r squared plus y squared over r squared is equal to 1. Now in this case, your a is r, and so is your b. So your semi-minor axis is r, and so is your semi-major axis is r. Or in other words, this distance is the same as that distance, and so it will neither be short and fat nor tall and skinny. It will be perfectly round. And so that's why the circle is a special case of an ellipse. So let me give you a slightly, it'll look a lot more complicated, and this is something you might see on an exam, but I just want to show you that this is just a shifting. Let's say we wanted to shift this equation, this ellipse. Let's say we wanted to shift it to the right by 5. So let's say we wanted to shift that to the right by 5. So instead of the origin being at x is equal to 0, the origin will now be at x is equal to 5, right? So a way to think about that is, what does this term have to be so that at 5, this term ends up being 0? Well, I'll actually draw it for you because I think that might be confusing. So if we shift that over the right by 5, the new equation of this ellipse will be x minus 5 squared over 9 plus y squared over 25 is equal to 1. So if I were to just draw this ellipse right now, it would look like this. It would look, I want to make it look fairly similar to the ellipse I had before. It would look just like that. Just shifted it over by 5. And the intuition, we learned a little bit in the circle video where I said, oh, well, you know, if you have x minus something, that means that the new origin is now at positive 5. And you could memorize that. You could always say, oh, if I have a minus here, that the origin is at a, is at the negative of whatever this number is. So it would be a positive 5. And, you know, if it had a positive, it would be the opposite of that. But the way to really think about it is now if we go to x is equal to 5, when x is equal to 5, this whole term x minus 5
equal to 0.
will behave just like this x term will here. When x is equal to 5, this term is 0, just like when x was 0 here. So when x is equal to 5, this term is 0, and then y squared over 25 is equal to 1. So you have y has to be equal to 5. Just like over here, when x is equal to 0, y squared over 25 had to be equal to 1. So y is equal to either positive or minus 5. So in either case, positive or minus 5. And I really want to give you that intuition. And then, let's say we wanted to shift this equation down by 2. Right? So if we wanted to shift it down by 2, so our new ellipse looks something like this. And this isn't anything, you know, when a lot of times you learn this in conic sections, but this is true of any function. When you shift things, you shift it this way. If you shift this graph to the right by 5, you replace all of the x's with x minus 5. And if you were to shift it down by 2, you would replace all the y's. Remember, we're shifting down by 2, so you would replace all the y's with y plus 2. So let me draw our new ellipse first, just to show you what I'm doing. So it's going to be a little bit, it's going to be shifted down by 2. So our new ellipse is going to look something like, that. So I'm shifting it down by 2. I'm shifting the yellow ellipse down by 2. So this equation, if I shift it down, well, the x is still where it was before, x minus 5 squared over 9, plus y plus 2 squared over 25 is equal to 1. And once again, the reason I know this is because now when y is minus 2, this whole term is 0, right? 0 when y equals minus 2. And when this term is 0, it behaves the same thing as when this term was 0. So when y is equal to minus 2, you get the same behavior, or you're at the same point in the curve, right here actually, as you are when y equals 0 in this one. So here. So it's not the same point. You can kind of view it the same part of the ellipse. Right? You're at kind of the maximum, you're at kind of the maximum width point on the ellipse here and here when y is equal to 2, and you were here at y equal to 0. And that's because when y equals minus 2, right? This is minus 2. And that's because when you put y equal minus 2 here, this whole term is 0, just like when y was 0 here. I don't want to make it too confusing. But just to kind of wrap it all up, sometimes you might see something like, graph the following: y minus 1 squared over 4 plus x plus 2 squared over 9 is equal to 1. And so the first thing you could say is, okay, this is just like the standard ellipse, y squared over 4 plus x squared over 9 is equal to 1. It's just like this, but it's shifted over, right? This one's origin is 0, 0, while this one's origin would be what? It would be the point x is minus 2 and y is 1. So if you were to graph this, your radius in your y direction is 2, right? 2 squared is equal to 4. Your radius in your x direction is 3. 3 squared is equal to 9. So let's see. So your x radius is actually larger than your y radius. It's going to be a little bit of a fat ellipse. It's going to be a little, actually, let me draw the axes first. So that's my, whoops. Let me draw it like this. That's my vertical axis. This is my x-axis. And so my center is now at minus 2, 1. So 1, 2. That's minus 2. And I go up 1. So it's up 1. That's the center of my ellipse. And now in the x direction, this is the x term, my x radius is 3. So the ellipse will go 3. This is kind of, it'll go 3 in that direction. This is its widest point, will be 3 in that direction. And then in the y direction, it'll go 2. So it'll go up 1, 2. So that's there. And then 1, 2. And it's there. So if I were to draw that ellipse, it would look something like this. Draw my best shot. It would look something like that. A little bit fatter than it is tall. And that's because your x radius is larger than your y radius.
Okay, fantastic. So from this video, at least we have learned how can we draw an ellipse from an equation like this. And what you could do is, first you write out the shifted center point or the source point or the original point, as I said, by doing this kind of thing. For example, y minus 1. That means you have to make the y equal to 1 so that 1 minus 1 equal to 0. And also for the x, how can we get the original point of this one? We have to say the x equal to negative 2 so that negative 2 plus 2 equal to 0. After we have got the original point, another thing that we need to do is to figure out the axis, the segment length of those axes. For example, for the y-axis, it should be the square root of 4, and for the x-axis, it should be the square root of 9, which is 3. So this is kind of simple. You don't have to do that much more. You don't have to do so much work to be able to draw your graph from that equation. Okay, let's get into the second video.
So we have an ellipse graphed right over here. What we're going to try to do is find the equation for this ellipse. So like always, pause this video and see if you can figure it out on your own. All right, so let's just remind ourselves the form of an equation of ellipse. So let's say our ellipse is centered at the point. So I'm going to speak in generalities first, and then we'll think about the specific numbers for this particular ellipse. So let's say the center is at the point h comma k, and let's say that you have a horizontal radius. So the radius in the x direction, horizontal radius is equal to a, And let's say your vertical radius, is equal to b, then the equation of this ellipse is going to be x minus h squared over your horizontal radius squared, so your radius in the x direction squared, plus, now we'll think about what we're doing in the vertical direction, y minus the y coordinate of our center, so y minus k squared, over the vertical radius squared, b squared, is equal to 1. So what are h and k and a and b in this situation? Well, h and k are pretty easy to figure out. The center of this ellipse is at the point, see, the x-coordinate is -4, and the y-coordinate is 3. So this right over here is -4, and this right over here is +3. And what is a going to be? Well, a is your horizontal radius, your radius in the horizontal direction, so it's the length of this line right over here, and we can see it's 1, 2, 3, 4, 5 units long. So a in this case is equal to 5, so this is going to be 5 squared. And b is our radius in the vertical direction. We can see it's 1, 2, 3, 4 units. So b is equal to 4. So that is 4. So we can rewrite this as, x minus -4, and we can simplify that in a second, x minus -4 squared over 5 squared over our horizontal radius squared, so it's going to be 25, plus y minus 3 squared, y minus the y coordinate of our center, y minus 3 squared, over our vertical radius squared, so b squared is going to be 16, and that is going to be equal to 1. And of course we could simplify this a little bit. If I subtract a negative, that's the same thing as adding a positive, so I can just, instead of saying x minus -4, I could just say x plus 4. And there you have it. We have the equation for this ellipse.
You know, after we have learned so many years of the English, we could generally find that after every word such as by or us, we do not use a verb anyway. We use the ing version of that verb. For example, by aiding something, us aiding something. I hope you get my idea. Ellipse graph from standard equation.
Whereas which ellipse is represented by the equation x minus 4 squared over 16 plus y minus 1 squared over 49 is equal to 1. And we're given a bunch of choices here. We're given 4 choices here. So let's just think about what's going on here. So the center of the ellipse is going to be 4, 1. How do I know that? Well, the equation of the ellipse is going to be x minus the x coordinate for the center squared over here over the horizontal axis, horizontal radius squared, plus y minus the y coordinate of the center squared over the vertical radius squared. So the center is going to be 4, 1. So the center here is not 4, 1. The center over here is not 4, 1. Not 4, 1. The only choice that has a center at 4, 1 is this one over here. So we already know this is the choice without even looking at the horizontal and the vertical radius. But we can verify that this works out because a horizontal radius right over here, notice it goes this orange line, which can represent the horizontal radius. It has a length of 4, and so the horizontal radius is 4. And so we see indeed that 16 is the horizontal radius squared. This is 4 squared. And if we look at the vertical radius,
Alright, this is quite simple. We don't need to look at it. As long as we know how to represent a ellipse with a graph, or how can we get some information from the graph to let's say to form a ellipse equation, then we're done. We don't have to know anything that beyond that.
Foci of an ellipse.
Foci of an ellipse. You know, back into my school time when I am still in high school, whenever whenever I made a crossing that related to the foci, I feel hopeless at that time because I don't know how to solve that kind of crossing. But for now, let's get into it and say, what is that?
Let's say we have an ellipse. The formula x squared over a squared plus y squared over b squared is equal to 1. And for the sake of our discussion, we'll assume that a is greater than b. And all that does for us is it lets us know this is going to be kind of a short and fat ellipse, or that the semi-major axis is going to, or the major axis is going to be along the horizontal and the minor axis along the vertical. And let's draw that. Let me draw this ellipse. I want to draw a thicker ellipse. Let's say that's my ellipse, and let me draw my axes. Okay, this is the horizontal right there. And there we have the vertical. And we've studied ellipse in pretty good detail so far. We know how to figure out its the semi-minor radius, which in this case we know is b. And that's the same b right there. And it's only the semi-minor radius because b is smaller than a. If b was greater, it would be the major radius. And then, of course, the major radius is a, and that distance is this right here. Now, another super interesting and perhaps the most interesting property of an ellipse is that if you take any point on an ellipse, and measure the distance from that point to two special points, which we, for the sake of this discussion, and not just for the sake of discussion, for pretty much forever, we will call the focuses or the foci of this ellipse. And these 2 points, they always sit along the major axis, so in this case it's the horizontal axis, and they're symmetric around the center of the ellipse. So let's just call these points, let me call this one F1, and this is F2, and it's for focuses, F2. So the super interesting, fascinating property of an ellipse, and it's often used as the definition of ellipse, is if you take any point on this ellipse and measure its distance to each of these 2 points. So let's say that I have this distance right here. Let's call this distance d1. And then I have this distance over here. So I'm taking any point on that ellipse, or this particular point, and I'm measuring the distance to each of these 2 foci. And this is d2. Maybe do it in a different color. I'm reusing all the colors. So this is d2, this whole line right here. That's d2. So when you find these 2 distances, you sum them up. So this d2 plus d1, this is going to be a constant that it actually turns out is equal to 2a. But it turns out that it's true anywhere you go on the ellipse. So let me make that point clear. And I'm actually going to prove to you that this constant distance is actually 2a, where this a is the same as that a right there. So just to make sure you understand what I'm saying. So let me take another arbitrary point on this ellipse. Let's take it right there. And if I were to measure the distance from this point to this focus, let's call that point D3. And then measure the distance from this point to that focus. Let's call that D4. If I were to sum up these 2 points, it's still going to be equal to 2a. Let me write that down. D3 plus D4 is still going to be equal to 2a. That's just neat. And actually, this is often used as the definition for an ellipse, where they say that the ellipse is a set of all points, or sometimes they'll use the word locus, which is kind of the graphical representation of the set of all points, that where the sum of the distances to each of these focuses is equal to a constant. And we'll play with that a little bit, and we'll figure out how do you figure out the focuses of an ellipse. But the first thing to do is just to feel satisfied that the distance, if this is true, that it is equal to 2a. And the easiest way to figure that out is to pick kind of these I guess you could call them the extreme points along the x-axis, here and here, right? We're already making the claim that the distance from here to here, let me draw that in another color, that this distance plus this distance over here is going to be equal to some constant number. And using this extreme point, I'm going to show you that that constant number is equal to 2a. So let's figure out how to do that. So one thing to realize is that these two focus points are symmetric around the origin. So whatever distance this is right here, it's going to be the same as this distance right there, right? Because these 2 points are symmetric around the origin. So this right here is the same distance as that, right? And of course, we have what we want to do is figure out the sum of this distance and this longer distance right there. Well, what's the sum of this plus this green distance? Well, this right here is the same as that. So this plus green, let me write that down. So let me write down these. Let me call this distance, I don't know, let me call it G, just to have, say, let's call that G, and let's call this H. If this is G, this is H, we also know that this is G because everything's symmetric. So what's G plus H? Well, that's the same thing as G plus H, which is the entire major diameter of this ellipse, which is what? Well, we know the minor radius is A, so this length right here is also A. So the distance, or the sum of the distance from this point on the ellipse to this focus plus this point on the ellipse to that focus is equal to G plus H, or this big green part, which is the same thing as the major diameter of this ellipse, which is the same thing as 2A. Fair enough. Hopefully that is good enough for you. Now the next thing now that we've realized that, is how do we figure out where these foci stand? Or if we have this equation, how can we figure out what these 2 points are? Let's figure that out. So the first thing we realize all of a sudden is that no matter where we go, it was easy to do it with these points. But even if we take this point right here and we say, okay, what's this distance? And then sum it to that distance, that should also be equal to 2a. And we could use that information to actually figure out where the foci lie. So let's say I have, let me draw another one. Okay. No, am I using the right? Okay, so this is, nope, don't want to draw a circle. So that's my ellipse, and then I want to draw the axes for clarity. And let me write down the equation again, just so we don't lose that. X squared over a squared plus y squared over b squared is equal to 1. Let's take this point right here. These extreme points are always useful when you're trying to prove something, or they can be. I don't want to say always. Now we said that we have these two foci that are symmetric around the center of the ellipse, right? This is F1, this is F2. And we've already said that an ellipse is the locus of all points, or the set of all points, that if you take each of these points' distance from each of the focuses and add them up, you get a constant number. And we figured out that constant number is 2a. So we figured out if you take this distance right here and add it to this distance right here, it'll be equal to 2a. Right? So we could say that, if we call this D1, this is D2, we know that D1 plus D2 is equal to 2a. Now, an interesting thing here is that this is all symmetric, right? This length is going to be the same. D1 is going to be the same as D2 because everything we're doing is symmetric. These two focal lengths are symmetric. This distance is the same distance as this distance right there. So D1 and D2 have to be the same. There's no way that you could. This is the exact center point of the ellipse. This ellipse is symmetric around the y-axis. So if D1 is equal to D2 and that equals 2a, then we know that this has to be equal to a and this has to be equal to a. Fair enough. I think we're making progress. And the other thing to think about, and we've already did that in the previous drawing of the ellipse, is what is this distance? This distance is the semi-minor radius, which we already learned is b. And this, of course, is the focal length that we're trying to figure out. This should already pop into your brain as a Pythagorean Theorem problem. So we have, we have the focal length, and we could do it on this triangle or this triangle. I'll do it on this right one here. This focal length is f. Let's call that f. F squared plus b squared is going to be equal to the hypotenuse squared, which in this case is d2 or a, which is equal to a squared. And now we have a nice equation in terms of b and a. We know what b and a are from the equation we were given for this ellipse. So let's solve for the focal length. The focal length, f squared, is equal to a squared minus b squared. So the focal length is going to be equal to the square root of a squared minus b squared. Pretty neat and clean and pretty intuitive way to think about something. So you just literally take the difference of these two numbers, whichever is larger, or whichever is smaller, you subtract from the other one. You take the square root, and that's the focal distance. Now let's see if we can use that to apply it to some real problems where they might ask you, hey, find the focal length or find the coordinates of the focuses. So let's say I had the equation x minus 1 squared over 9 plus y plus 2 squared over 4 is equal to 1. So let's just graph this first of all. This could be interesting. So I'll draw the axes. That's the x-axis. This is the y-axis. And we immediately see, well, what's the center of this? The center is going to be at the point 1, negative 2. And if that's confusing, you might want to review some of the previous videos. Center is at 1. X is equal to 1. Y is equal to minus 2. That's the center. And then the major axis is the x-axis, because this is larger. And so b squared or a squared is equal to 9. Or the semi-minor radius is going to be equal to 3. So if we go 1, 2, 3, 1, 2, 3, go there, then you have 1, 2, 3, no, 1, 2, 3, 1, 2, 3. I think this, let's see, 1, 2, 3, you go there, roughly. And then in the y direction, the semi-minor radius is going to be 2, right? The square root of that. So b is equal to 2. So you go up 2, then you go down 2. And this ellipse is going to look something like, pick a good color, it's going to look something like this. Fair enough. And what we want to do is we want to find out the coordinates of the focal points. So the focal points are going to sit along the semi-major axis, right? And we need to figure out these focal distances, and then we can essentially just add and subtract them from the center, and then we'll have the coordinates. Well, we just showed to you, or hopefully I showed to you, that the focal length, or this distance f, the focal length is just equal to the square root of the difference between these two numbers, right? So it's the square root of 9 minus 4. So the focal length is equal to the square root of 5. So if this point right here is the point, we already showed that. This is the point, the center of the ellipse is the point 1 comma minus 2. The coordinate of this focus right there is going to be 1 plus the square root of 5 comma minus 2. And the coordinate of this focus right there is going to be 1 minus the square root of 5 comma minus 2. And all I did is I took the focal length and I subtract, since we're along the major axis or the x-axis, I just added.
Okay, before he goes any way farther, I think I just lost my mind to follow him. So I need to recover this for a little bit. Okay, it seems like we need to go back for a little bit. I just watch it again.
I lie. So let's say I have, let me draw another one. Okay, no, am I using the right? Okay, so this is, nope, don't want to draw a circle. So that's my ellipse. And then I want to draw the axes for clarity. And let me write down the equation again, just so we don't lose that. X squared over a squared plus y squared over b squared is equal to 1. Let's take this point right here. These extreme points are always useful when you're trying to prove something. Or they can be, I don't want to say always. Now we said that we have these two foci that are symmetric around the center of the ellipse. Right? This is F1, this is F2. And we've already said that an ellipse is the locus of all points, or the set of all points, that if you take each of these points' distance from each of the focuses and add them up, you get a constant number. And we figured out that constant number is 2a. So we figured out if you take this distance right here and add it to this distance right here, it'll be equal to 2a. Right? So we could say that, if we call this D, d1. This is d2. We know that d1 plus d2 is equal to 2a. Now, an interesting thing here is that this is all symmetric, right? This length is going to be the same. d1 is going to be the same as d2 because everything we're doing is symmetric. These two focal lengths are symmetric. This distance is the same distance as this distance right there. So d1 and d2 have to be the same. There's no way that you could. This is the exact center point of the ellipse. This ellipse is symmetric around the y-axis. So if d1 is equal to d2 and that equals
Okay, so this is a special case where you has a symmetric triangle, I guess. Yeah, since you got two sides of a triangle and they have the same length.
2a, then we know that this has to be equal to a and this has to be equal to a. Fair enough. I think we're making progress. And the other thing to think about, and we've already did that in the previous drawing of the ellipse, is what is this distance? This distance is the semi.
Okay, so this is where the Pythagorean theory was applying about. When you have a symmetric triangle, you could do this. For example, how can you get the length of the focus 2?
Minor
I mean, how can you get the length?
radius, which we already.
How can you get the length of the segment from the original point to the f2? Well, you use the Pythagorean method, which is square root of a squared minus b squared. This green line is the b, has the length of b. So for now, you should probably understand where the f equal to square root of 9 minus 4 comes from. It comes from the previous application of the Pythagorean theory. Then let's go to the next one. This one is called the Introduction to
Hyperbolas.
Hyperbolas.
Let's see if we can learn a thing or two about the hyperbola. Hyperbola. And
Okay, this is kind of interesting. We just made a bug of this website.
And out of all of the conic sections, this is probably the one that confuses people the most because it's not quite as easy to draw as the circle and the ellipse because you got to do a little bit more algebra. But hopefully over the course of this video, you'll get pretty comfortable with that, and you'll see that hyperbolas in some way are more fun than any of the other conic sections. So just as a review, and I want to do this just so you see the similarity in the formulas or the kind of the standard form of the different conic sections. If you have a circle centered at 0, its equation is x squared plus y squared is equal to r squared. And we saw that this could also be written as, and I'm doing this because I wanted to show that this is really just the same thing as the standard equation for an ellipse. If you divide both sides of this by r squared, you get x squared over r squared plus y squared over r squared is equal to 1. And so this is a circle. And once again, just as a review, a circle, all of the points on the circle are equidistant from the center. Or in this case, you could kind of say that the major axis and the minor axis are the same distance, that there isn't any distinction between the two. You're always an equal distance away from the center. So that was a circle. An ellipse was pretty much this, but these two numbers could be different because your distance from the center could change. So it's x squared over a squared plus y squared over b squared is equal to 1. That's an ellipse. And now you'll see that and I'll skip parabola for now because parabola is kind of an interesting case and you've already touched on it. So I'll go in more depth in that in a future video. But in a hyperbola is very close in formula to this. And so there's two ways that a hyperbola could be written. And I'll do those two ways. So it could either be written as x squared over a squared minus y squared over b squared is equal to 1. Notice the only difference between this equation and this one is that instead of a plus y squared, we have a minus y squared here. So that would be one hyperbola. The other one would be if the minus sign was the other way around. If it was y squared over b squared minus x squared over a squared is equal to 1. So now the minus is in front of the x squared term instead of the y squared term. And what I want to do now is try to figure out how do we graph either of these parabolas, and maybe we'll do both cases. And in a lot of textbooks, or even if you look it up over the web, they'll give you formulas. But I don't like those formulas. One, because I'll always forget it, and you'll forget it immediately after taking the test. You might want to memorize it if you just want to be able to do the test a little bit faster, but you'll forget it. And the second thing is, not only do you forget it, but you'll probably get confused because sometimes they always use the a under the x and the b under the y, or sometimes they always use the a under the positive term and the b under the negative term. So if you just memorize, oh, a divided by b, that's the slope of the asymptote and all of that, you might be using the wrong a and b. So I encourage you to always kind of reprove it to yourself. And that's what we're going to do right here. And it actually doesn't take too long. So these are both hyperbolas. And what I like to do whenever I have a hyperbola is solve for y. So in this case, I get, let's see, if I subtract x squared over a squared from both sides, I get, let me just change the color, I get minus y squared over b squared. Right, that stays there, is equal to 1 minus x squared over a squared. And then let's see, I want to get rid of this minus and I want to get rid of this b squared. So let's multiply both sides of this equation times minus b squared. Right? If you multiply the left-hand side times minus b squared, the minus and the b squared go away, and you're just left with y squared is equal to minus b squared. And then minus b squared times a plus, that becomes a plus b squared over a squared x squared. We're almost there. And then you get y is equal to, and I'm doing this on purpose, the plus or minus square root, because it can be the plus or minus square root, of, and let's switch these around just so I have this term first, the positive term first. B squared over a squared x squared minus b squared. Now, what is this? You said, Sal, you said this was simple. I'm solving this. This looks like a really complicated thing. But remember, we're doing this to figure out the asymptotes of the hyperbola, just to kind of give you a sense of where we're going. Let me do it here. I'll do the other. Well, actually, I want to do that other hyperbola. So a hyperbola, if that's the x, that's the y-axis. It has two asymptotes. And the asymptotes, they're these lines that the hyperbola will approach. So if those are the two asymptotes, and they're always the negative slope of each other. We know that this hyperbola is either, and we'll show it in a second which one it is. It's either going to be, it's going to look something like this, where as we approach infinity, we get closer and closer to this line and closer to that line. And here, it's either going to look like that. I didn't draw it perfectly. It never touches the asymptote. It just gets closer and closer and closer, arbitrarily close to the asymptote. It's either going to look like that, where it's kind of on, opens up to the right and the left, or our hyperbola is going to open up, and down. And once again, as you go further and further, an asymptote means that it's just going to get closer and closer to one of these lines without ever touching it. But it'll get infinitely close as you get infinitely far away, as x gets infinitely large. So in order to figure out which one of these things is, let's just think about what happens as x becomes infinitely large. So if I draw, so as x approaches infinity. So as x approaches infinity, or x approaches negative infinity, so I'll say plus or minus infinity, right? It doesn't matter because when you take a negative, this gets squared. So this number becomes really huge as you approach positive or negative infinity. And you'll learn more about this when we actually do limits. But I think that's intuitive, that this number becomes huge. This number is just a constant. It just stays the same. So as x approaches positive or negative infinity, as it gets really, really large, y is going to be approximately equal to, well, I don't want to do that. Actually, I think that's congruent. I think this is, I always forget notation. Approximately, this just means not exactly, but approximately equal to, when x approaches infinity, it's going to be approximately equal to the plus or minus square root of b squared over a squared x squared, right? And that is equal to, now you can take the square root of this. You couldn't take a square root of this algebraically, but this you can. This is equal to plus or minus b over a x. So that tells us essentially what the two asymptotes are, where the slope of one asymptote will be b over ax. This could, you could view that as positive b over ax, and the other one would be minus b over ax. And I'll do this with some examples, so it makes it a little.
So as for now, here's an interesting thing he did. So how does he get that line? I mean that original line, which the function's value will never approach it, will never reach it, but keeps approaching it. How he get that two line? Well, he's using some infinity idea. What he did is to input that infinity, either a positive infinity or a negative infinity to that x, and then as the first term b squared divided by a squared times a squared. Since this item can be very large, in the end, the minus b squared would be nothing. So what he did is just drop it. So after the dropping, he can finally figure out the square root of this item. Then he gets the idea, which is a positive or negative b divided by a times x. To be honest, I never know this before. Back into my school, in my school time, the teacher, what the teacher says is that you just have to memorize those equations on your book, but that's not true. I cannot remember that since I do not understand that. Alright, enough talking. Let's go on with this video.
Clearer. But so we know what the asymptotes look like. It's these two lines, right? Because it's a plus bax is one line, y equals plus bax. Let's say it's this one. This asymptote right here is the y is equal to plus b over ax. I know you can't read that. And then the downward sloping asymptote, we could say, is y is equal to minus b over ax. So those are two asymptotes, but we still have to figure out whether the hyperbola opens up to the left and right, or does it open up and down. And there, at least, there's two ways to kind of do this. One, you see, well, this was an approximation. This is what you approach as x approaches infinity. But we see here that even when x approaches infinity, we're always going to be a little bit smaller than that number because we're subtracting a positive number from this, right? We're subtracting a positive number and then we're taking a square root of the whole thing. So we're always going to be a little bit lower than the asymptote, especially when we're in kind of the positive quadrant, right? So to me, that's how I like to do it. I think, we're always, at least in the positive quadrant, it gets a little more confusing when you go into the other quadrants. We're always going to be a little bit lower than the asymptote. So we're all going to approach from the bottom there. And since you're there, it's going to be like this and approach this asymptote. And then since it's opening to the right here, it's also going to open to the left. The other way to test it, and maybe this is more intuitive for you, is to figure out, in our original equation, could x or y equal to 0? Because when you open to the right and left, notice you never get to x equal to 0. You always get to y equals 0 right here and here, but you never get to x equals 0. And actually, your teacher might want you to plot these points, and there you just substitute y equals 0. And that you could just look at the original equation. Actually, you could even look at this equation right here. Could x ever equal 0 if you look at this equation? If x is equal to 0, this whole term right here would cancel out, and you'd just be left with a minus b squared, which is you're taking b squared and you put a negative sign in front of it. So that's a negative number. And then you're taking the square root of a negative number. So we're not dealing with imaginaries right now. So you can never have x equal to 0. So, but y could be equal to 0, right? You could set y equals 0 and then you could solve for it. So in this case, and actually let's do that. If y is equal to 0, you get 0 is equal to the square root of b squared over a squared x squared minus b squared. You could square both sides. You get b squared over a squared x squared minus b squared is equal to 0. I know this is messy. So then you get b squared over a squared x squared is equal to b squared. You could divide both sides by b squared, I guess. You get a 1 and a 1. And then you could multiply both sides by a squared. You get x squared is equal to a squared, right? And then you get x is equal to the plus or minus square root of a. So this point right here is the point a comma 0, and this point right here is the point minus a comma 0. Let's go back to the other problem. I have a feeling I might be running out of time. So notice that when the x term was positive, our hyperbola opened to the right and the left. And you could probably guess from deductive reasoning that when the y term is positive, which is the case in this one, we're probably going to open up and down. And let's just prove that to ourselves. So let's solve for y. You get y squared over b squared. We're going to add x squared over a squared to both sides. So you get equals x squared over a squared plus 1. Multiply both sides by b squared. Y squared is equal to b squared over a squared x squared plus b squared. Got to distribute the b squared. Now take the square root. I'll switch colors for that. So y is equal to the plus or minus square root of b squared over a squared x squared plus b squared. And then once again, I've run out of space. We can make that same argument that as x approaches infinity, as x approaches positive or negative infinity, x approaches positive or negative infinity, this equation, this little constant term right here isn't going to matter as much. So you're just going to take the square root of this term right here, which is essentially b over ax plus or minus b over ax. And once again, those are these same two asymptotes, which I'll redraw here. That line and that line. But in this case, we're always a little bit larger than the asymptotes. We're always a little bit larger than the asymptotes, especially in the positive quadrant. That tells us that we're going to be up here and down there. And another way to think about it, in this case, when the hyperbola is vertical, or it's a vertical hyperbola where you're always kind of, it opens up and down, you notice x could be equal to 0, but y could never be equal to 0. And that makes sense too, because if you look at our original formula right here, x could be equal to 0. If x was 0, this would cancel out, and you could just solve for y. But if y were equal to 0, you'd have minus x squared over a squared is equal to 1. And then you would have, if you solve this, you would get x squared is equal to minus a squared. And we're not dealing with imaginary numbers, so you can't square something and you can't get a negative number. So once again, this would be impossible. So that's the other clue that tells you it opens up and down, because in this case, y could never equal 0. Anyway, you might be a little confused because I stayed abstract with the b's and the a's. In the next couple of videos, I'll do a bunch of problems where we draw a bunch of hyperbolas, ellipses, and circles with actual numbers. See you soon.
Which of the following graphs can represent the hyperbola y squared over 9 minus x squared over 4 is equal to 1?
Alright, before he do that, let me do it first. According to the last video, it says that if the y here is a positive number, that means the hyperbola should get changed as the y-axis. So it can be either A or C, but which one is the right answer? We can give it some, let's say, special point. For example, how about we set the x equal to 0? If we do so, we'll get a y squared equal to 1 over 9. Then the y would be equal to positive or negative 1/3. Oh, I'm wrong. So if we set the x equal to 0, then the y squared should be equal to 9. Then the y could be either positive or negative 3. So let's say for this problem, we should choose option A.
And we have our 4 choices here. Choices A and C open up to the top and the bottom. You can see down one, or if y over 0 is that it is actually plus or minus 3. So over here, we're on this hyperbola, the y over 4 is equal to negative 1. The enter. So that's what. So y is never positive. That, and what the actual vertices are, we saw that the points have 0 plus or minus 3 on the graph. It has 0 plus or minus 2. So we can feel pretty good about choice A.
Okay, so how do you feel like? I can solve this problem within 10 seconds, but the Kehan, the author of this video, have spent 5 minutes to solve this kind of problem. So, this is something people would argue. They would say that some genius or some smart people normally would solve a problem in a very quick speed and also with a high accuracy. Why? It is because they know the behind the row. They have mastered that kind of row. So they are solving those problems without thinking too much, just like me. But if I do not know those rows before, if I didn't watch all those videos that we just watched, then we can never solve this problem.
So we're asked to choose the equation that can represent the hyperbola graphed below. And so
okay, another this kind of example. Can we solve it? At the first, I would say for this one, the hyperbola is measured on the x-axis, so the x item must be a positive one. So you can either A or C. Then I'm going to set the y equal to 0. If we set that equal to 0, the x should be equal to 5. And for this case, only the option A is the right one. So I can just jump the video to the end to say what he choose. And in the end, we are right. He chose A. This is simple. Okay, let's get into the next section.
Foci of a hyperbola.
Foci of a hyperbola. Hyperbola. Remember this pronunciation, because you're gonna use it very much. This is something that you have to know.
In the last video, we learned that an ellipse can be defined as the locus of all points where the sum of the distances to two special points called foci, and let me draw this all out, so that's my x-axis. The sum of the distance to these two special points called focuses or foci is a constant. So if this is my ellipse, let me draw it out. Oh, that looks about, I want it to be right around, that looks about right. It's centered at the origin. Doesn't have to be, but for our purposes, let's make it centered at the origin. If this is one focus point right here, and this is the other focus point, this ellipse could be defined as a set of all points, or the locus of all points, or if I take the distance of any one of these points that exist on the ellipse, and take the distance to each of the locuses, each of the focuses. So if I take nope, I don't want to do that. If I take that distance and add it to this distance, so let's call those, I don't know, let's call this D1, nope, too thick. Let's call that D1, this is D2, that's going to be equal to a constant number along the whole ellipse. So if I take a random, let's say another point along the ellipse, say I take this point right here, and if I were to sum this distance, if I were to sum this distance to that distance, so let's call this right here D3, this is D4. The sums of these distances to the focus along this ellipse are going to be a constant. So in this case, D2 plus D1, this plus that, is going to be equal to D3 plus D4, D3 plus D4. And this would be true wherever you go along the whole ellipse. And we learned in the last video that this quantity is actually going to be equal to 2a, where a is the distance, the semi-major radius. If this is the formula for the ellipse, this is where the a comes from. X squared over a squared plus y squared over b squared is equal to 1. And we learned that the focal distance, or the distance from the center of the ellipse, which is this distance right here, that focal distance is just the square root of the difference of these two numbers. So it's just, so we could call, if this is the focal distance from here to here, it's just equal to the square root of, if a is larger, then it would be a squared minus b squared, which is the case in this ellipse. If we have a vertical ellipse, and I really didn't cover it in the last video, but let me just show you what it would look like. Let's say that the ellipse looks something like this. Let me see. All right. I'll use blue. Let's say the ellipse look like that. In this case, our semi-major radius is now in the y direction. So this is b, this is a, and in this case, b is greater than a, right? Because the ellipse is tall and skinny. And in this case, the focuses are going to they're always going to lie along the major axis. And in this case, the major axis is the vertical axis. So the focuses are going to sit here and here. And in this case, the focal lengths are going to be vertical down from the origin and vertical up from the origin. And we get, instead of it being a squared minus b squared, now since b is larger than a, the focal length, which is this, the focal length is going to be equal to b squared minus a squared. Fair enough. Now I did all of that to kind of compare it to what we're going to cover in this video, which is the focus points or the foci of a hyperbola. And a hyperbola, it's very close to an ellipse. I mean, you could probably guess that, because if this is an equation of an ellipse, this is the equation of a hyperbola. X squared over a squared minus y squared over b squared is equal to 1. Or we could switch these around where the minus is in front of the x instead of the y. And we could cover that in a second. But this hyperbola looks something like this. Let me see if I can draw it. Let's see if I draw the axes. Then I want to draw the asymptotes. You could prove it. You could look at some of the previous videos. But the asymptotes for this hyperbola are going to be y is equal to plus or minus b over ax. So it's going to look, I'll just draw them as kind of tilted lines. So it would look something like that, something like, nope, I want to make it something like that. Those would be the asymptotes. This one's centered at the origin because it hasn't been shifted. And then that's those two lines right there. And then this is what I call kind of a horizontal hyperbola. The way you can think about that is, well, if you solve for y, you'll see that you're always going to be a little bit lower than the asymptote. The other option is you say, okay, can x or y equal 0? Well, if y is equal to 0, that puts us along the x-axis. Right? And you get x squared over a squared is equal to 1, or x. So if y is equal to 0, you get x squared over a squared is equal to 1, which means that x squared is equal to a squared, which means that x is equal to plus or minus a. So the points a comma 0, so this is the point a comma 0, and the point minus a comma 0 are both on this hyperbola. And since they have to kind of be contained by these asymptotes.
So how he calculated out the value of a? Well, what he did is just replace or substitute the y with the value 0. So when you set the y equal to 0, you get the x value, which is a positive 1 and the negative 1.
Let's never go through it. You know that this is going to be a hyperbola that opens to the left and the right, so it'll look something like this. let me use this color. So it looks something. This is the hard part. So it'll get closer and closer on that side, and then you can kind of view this as one of the vertexes or vertices of the hyperbola. And it'll go like that. Where this distance, and notice the similarity here with the ellipse. This distance right here, let me do it in a more vibrant color. This distance right here, between these two, I guess you could kind of, the elbows of the two ellipses, that distance right there, this is A, and this is also A. So you have a 2A distance, which is very similar to this situation, where this distance is A, and this distance is A. So your distance between the two left and right points in a horizontal ellipse is the same as the distance between the two left and right points on a hyperbola. It's just the hyperbola opens outward while the ellipse opens inward. Fair enough. But the whole point of this video is to discuss foci. And you might have guessed, and I did touch on it in the last video, that hyperbola also have foci. But they're going to be to the right and the left of these 2 points. So this is let me do them in a bright color because I want you to see them. Let's say that those are the 2 foci. And a hyperbola, and notice the difference. An ellipse, one of the definitions of an ellipse, was the locus of all points, or the set of all points, where the distance from each of those points, the sum of the distance from each of those points to the 2 foci, is a constant. Now the definition of a hyperbola, one of the definitions of a hyperbola, can be the locus of all points, where you take the difference, not the sum, you take the difference of the distances between the 2 foci.
Here we go. What do they call the 2 rated points out there? They call the foci. It's kind of weird. If I were Zen, I would call it focus point or just 2 points. I won't say that it's foci. It's kind of weird. So it seems like they just created a line for the 2 points out there.
So let me write that down. So if this is D1 and this is D2, so you have a situation, and we could take the absolute value of the difference, because they might at some points D1 will be longer than D2 if you're on this curve. If you're on this curve, D1 will be shorter than D2. So D1 minus D2, the absolute value, is going to be equal to constant. In the ellipse situation, D1 plus D2 was a constant. So they're very closely related. You're in the ellipse, you're taking the sum of the distances to the focus points and saying it's a constant. In a hyperbola, you're taking the difference of the distances to the focus points and saying that's a constant. So this number right here is going to be the exact same thing as if I took a point right here. And I'm picking these points arbitrarily as long as they're on the hyperbola. And if I call these 2 points, let's call these D3 and D4. The difference between D1 and D2 is the same thing as the difference between D3 minus D4. This is going to be a constant the entire way around the ellipse. And so the next question is, well, what is this constant going to be equal to? And this is where it's useful to find a point where you can kind of get the intuition. And we did it with the ellipses, where we said, oh, if we take these points, we used logic in the last video to say, oh, the sum of the distance between this and this, that sum is going to be equal to, is going to be equal to 2a, or the distance of the semi-major axis, right? Because this distance was the same as this distance, so this plus this is the same thing as this plus that, which is 2a, right? So the entire time, the constants, the sum of the distances to the 2 foci was equal to 2a. Now in the hyperbola, what is the difference of the distances to the 2 foci? So let's take this point right here on the hyperbola, and we're saying, so what is, let me do a good color. What is the magenta distance? That's the distance to that foci. Minus this, or let me pick another color, minus this, light blue distance. This magenta distance minus this light blue distance. So we can make a very similar argument that we made in the ellipse situation. This light blue distance is the same, the distance from this vertex, or from this, I guess, this leftmost point of this rightward opening hyperbola to this focus, is the same as this distance. Because the hyperbola is symmetric around the origin, or the focal length is the same on either side of the center of the hyperbola, depending on how many you view it. But I think that's that's not too much of a stretch of a statement for you to accept. So if this distance is the same as this distance, then the magenta distance minus this blue distance is going to be equal to this green distance, right? And this green distance is what? That's 2a. We saw that at the beginning of this video. So this, once again, is also equal to 2a. Anyway, I'll leave you there right now. Actually, well, And let's actually just do one problem, just because I like to make one concrete. Because I told you at the beginning that if you wanted to find, let's say if you have an ellipse, so this is an ellipse, x squared over a squared plus y squared over b squared is equal to 1. We learned that over b squared. This is an ellipse. We learned that the focal length is equal to the square root of a squared minus b squared. Now for a hyperbola, you kind of see that there's a very close relation between the ellipse and the hyperbola, and it is kind of a fun thing to ponder about. And a hyperbola's equation looks like this: x squared over a squared minus y squared over b squared, or it could be y squared over b squared minus x squared over a squared is equal to 1. It turns out, and I'll prove this to you in the next video, it's a bit of a hairy math problem, that the focal length of a hyperbola is equal to the square root of the sum of these two numbers, is equal to the sum of a squared plus b squared. So if I were to give you, so notice the difference, it's just a difference in sign. You're taking the difference of those kind of two denominators, and now you're taking the sum of the two denominators. So if I were to give you the following hyperbola: x squared over 9 plus y squared over 16 is equal to 1. Well, the first thing you do, we could just figure out the focal length just by plugging into the formula. The focal length is equal to the square root of a squared plus b squared. This is a squared, right? A is 3, b is 4. So 9 plus 16 is 25, which is equal to 5. And so if we were to graph this, let me see. So that's my y-axis. That's my x-axis. And the focal length is the distance to in this case, to the left and the right of the origin. If it was kind of an up and down opening hyperbola, it would be above and below the origin. So this is a, oh sorry, this shouldn't be a plus. We're doing it with a hyperbola. That should be a minus. Don't want to confuse you. What I had written before with a plus, that would have been an ellipse. A minus is a hyperbola. So the two asymptotes, this is centered at the origin, it hasn't been shifted, are going to be 16 over 9. So it's going to be fairly steep asymptotes. It's going to look something like that and that. Those are the two asymptotes. The two vertex points are at 2 times a. A is 3, right? A squared is equal to 9. B squared is equal to 16. So this is a center. So the two vertex points, this is 3 minus 3. And then the focal points are going to be at from the center 5 to the right. So it's going to be right here. So that's 5 comma 0. So it's 5 comma 0. And minus 5 comma 0. This is minus 3, and this is 3. So if we were to graph it, it would look something like this. There you go. And if you were to take an arbitrary point on that hyperbola and take this distance and subtract that from that distance, that will be a constant number that would be exactly equal to 2a, or exactly equal to 6 in this particular example. Anyway, hopefully I didn't confuse you too much with that little sign error near the end of the video. But in the next video, I'll prove to you this formula, which is a little bit of a hairy algebra, but it's fun to do regardless.
Wait, so he just did something, right? So, what he did is to use a and b to calculate out the both side points. That's how they call it. But he didn't tell us how where that formula was come from. So in the next video, what he did is to give us a proof.
In the last video, I told you that if I had a hyperbola with the equation x squared minus for the square root of the sum of these two numbers, the square root of a squared plus b squared. In this video, I really just want to show you that. And actually, just so you know, this equation right here, this is a particular hyperbola that opens to the left and the right, and that's because those are the asymptote points, those would be the axes. And that's because the x term is positive. If the y term was positive and the x term had a negative sign, then the hyperbola would open upwards and downwards like that. And the proof that I'm showing you in this video, it's just a bunch of algebra really, is identical in the y case. You just switch around the x's and the y's. But I just wanted to make sure you realize that I'm just doing a particular case of a hyperbola that opens to the left and the right. I could call it a horizontal hyperbola instead of a vertical one. But I wanted to make it clear that there is another type of hyperbola. But anyway, let's draw a graphical representation of all this just to make sure we understand, or we re-understand, or better understand what the foci points are and where they sit on the hyperbola. So if those are my axes, the asymptotes of this hyperbola are the lines y is equal to plus or minus b over a. We've gone, oh, whoops, not using my line tool. So that's one, and that's the other asymptote. And then, so the hyperbola will look something like this. It'll look something like that. It's going to intersect at a comma 0 right there. This is going to be a comma 0, and then intersect at minus a comma 0. We saw all of this in the previous video. It'll look something like that. And then the focus points are going to sit out here someplace, there and there. And the focal length this a squared plus b squared, the square root of a squared plus b squared, that's just this distance right here. That distance is the focal length. So this is going to be the point f0, and this is going to be the point minus f0. Now, we learned in the last video that one of the definitions of a hyperbola is the locus of all points, or the set of all points, where if I take the difference of the distances to the two foci, that difference will be a constant number. So if this is the point x comma y, and it could be any point that satisfies this equation, it's any point on the hyperbola, we know, or we are told, that if we take this distance right here, let's call that d1, and subtract from that the distance to the other foci, call that d2, that number is a constant regardless of where we are on the hyperbola. In fact, the locus of all points are, the hyperbola in fact is all of the points that satisfy that condition. And we learned in the last video, just by taking the distance, the difference of the distance, we picked this point, we said, okay, what's that distance minus that distance? And we figured out that it's 2a. So d1 minus d2 is equal to, I'm going off the video screen, d1 minus d2 is equal to 2a. So let's use this fact right here, that d1 minus d2 is equal to 2a, to try to prove this right there. So the first thing to do is figure out what d1 and d2 are, just using the distance formula. So what's d1? d1 is the distance between this point and this point minus f0. So what you do is this, we just use the distance formula, which is really just the Pythagorean theorem. So it's the difference of the x's. It's the x distance, so it's x minus f squared, plus the y distances, y minus 0. So that's just y squared. Take the square root of that. So that's d1 right there, d1. And we want to subtract from that d2, right? The difference of the distances, and in this case d1 is definitely bigger than d2. Well, you could take the absolute value if you didn't want to worry about that. And so here we get the square root of x minus f squared, plus y squared. And what does that equal to? Well, we said that equals to 2a. That equals this distance right here. So that is equal to 2a. Now let's see if we can simplify this at all. Well, an interesting thing to do might just be to put this on the other side of the equation. And this can get hairy, so I really hope I don't make any careless mistakes. So this becomes, and I might write small to save space. This becomes x plus f, right, minus minus squared, plus y squared is equal to 2a plus the square root of x minus f squared plus y squared. Now, to get rid of these radicals, let's square both sides of this equation. The left-hand side, if you were to square it, just becomes x plus f squared plus y squared. And then to square this, we square the first term, which is 4a squared. Then we multiply the two terms and multiply that by 2, right? We're just taking this whole thing and squaring it. So that's, and this is just a review of kind of binomial algebra. So this is equal to plus, so 2a times this times 2 is 4a times the square root of x minus f squared plus y squared. Don't want to lose that squared right there. And then we square this term. And this is just multiplying a binomial. So that's equal to, you just get rid of the radical sign. And let me stay in that color for now. That's equal to x minus f squared plus y squared. And already it looks like there's some cancellation that we can do. We can cancel out. There's a y squared on both sides of this equation. So let's just cancel those out. Subtract y squared from both sides of the equation. And let's multiply this term out. So this right here is x squared plus 2xf plus f squared. And then that is equal to 4a squared plus 4a times the square root of x minus, actually, well, let me just write it. X minus f squared plus y squared. And then multiply this out. Plus x squared minus 2xf plus f squared. And then let's see, what can we cancel out? Well, we have an x squared on both sides of this. We subtract x squared from both sides of the equation. We have an f squared on both sides of the equation, so let's cancel that out. And see, what can we do to simplify it? So we have a minus 2xf and a plus 2xf. Let's add 2xf to both sides of the equation, or bring this term over here. So if you add 2xf to both sides of this equation, see, my phone is ringing. Let me turn it off. If you add 2xf to both sides of this equation, what do you get? You get 4xf. Remember, I just brought this term over this left-hand side, is equal to 4a squared plus 4a times the square root of x minus f squared plus y squared. It's easy to get lost in the algebra. Remember, all we're doing, just to kind of remind you of this whole point was. We're just simplifying the difference of the distances between these 2 points, and then see how it relates to the equation of the hyperbola itself, the a's and the b's. So let's take this 4a, put it on this side. So you get 4xf minus 4a squared is equal to 4a times the square root of, let's just multiply this out because we'll probably have to eventually, x squared minus 2xf plus f squared plus y squared. That's this just multiplied out. That's the y squared right there. We could divide both sides of this by 4. All I'm trying to do is just simplify this as much as possible. So then this becomes xf minus a squared is equal to a times the square root of this whole thing, x squared minus 2xf plus f squared plus y squared. And now we could square both sides of this equation right here. And then if you square both sides, this side becomes x squared f squared minus 2a squared xf plus a to the 4th. That's this side squared. And that's equal to, if you square the right-hand side, a squared times the square of the square root is just that expression, x squared minus 2xf plus f squared plus y squared. This really is quite hairy. And let's see what we can do now to let's divide both sides of this equation by a squared, and then you get x squared, I'm really just trying to simplify this as much as possible, over a squared minus, so the a squareds cancel out, minus 2xf plus a to the 4th divided by a squared. Well, that's just a squared. So a squared is equal to x squared minus 2xf plus f squared plus y squared. Well, good. There's something to cancel out. There's a minus 2xf on both sides of this equation. So let's cancel that out. Simplify our situation a little bit. And let's see. We have, so what we could do is subtract this x squared from this. So you get, let me rewrite it. So you get x squared f squared over a squared minus x squared. And let's bring this y to this side of the equation too. So minus y squared. That's all I did. I just brought that to that side. And then let's bring, and I'm kind of skipping a couple of steps, but I don't want to take too long. Let's take this a and put it on that side of the equation. So we took the x and the y, and we subtracted that from both sides of the equation, so they ended up on the left-hand side. And then if we subtract a squared from both sides of this equation, this is a fatiguing problem, then you get f squared minus a squared. I think we're almost there. This can simplify to, let's see, we can factor out the x squared. This becomes f squared over a squared minus 1 times x squared. I just factored out the x squared there. Minus y squared is equal to f squared, the focal length squared, minus a squared. And let's see, let's divide both sides of the equation by this expression right there. And we get, and this should start to look familiar, we get f squared over a squared minus 1 x squared divided by f squared minus a squared minus y squared over f squared minus a squared is equal to 1, right? I divided both sides by this, so I just get a 1 on this right-hand side. Let's see if I can simplify this. If I multiply the numerator and the denominator by a squared, right? As long as I multiply the numerator and the denominator by the same number, I'm just multiplying by 1, so I'm not changing anything. So if I do that, the numerator becomes f, if I multiply it, it becomes f squared minus a squared. I'm just multiplying that times a squared. And the denominator becomes a squared times f squared minus a squared. And all of that times x squared minus y squared times f squared minus a squared is equal to 1. This cancels with this, and we get something that's starting to look like the equation of a hyperbola. My energy is coming back. It seems like I see the light at the end of the tunnel. We get x squared over a squared minus y squared over f squared minus a squared is equal to 1. Now this looks a lot like our original equation of the hyperbola, which was x squared over a squared minus y squared over b squared is equal to 1. In fact, this is the equation of the hyperbola, but instead of writing b squared, since we wrote it, we essentially said, what is the locus of all points where the difference of the distances to those two foci is equal to 2a? And we just played with the algebra for a while. It was pretty tiring, and I'm impressed if you've gotten this far into the video. And we got this equation, which should be the equation of the hyperbola. And it is the equation of the hyperbola. It is this equation. So this is the same thing as that.
Alright, so finally I got it. I got the idea of how all it works. Actually, you have to do the transformation or the algebra work a lot to be able to get the final answer. And for each step when you're doing the algebra transformation, there has a lot of opportunity that you may go wrong. So nobody could assure that you would get the right answer in the end. But how he got that right answer, was that because he's lucky? No, it's not. It's because he did that before, and he know the right combination that could end up with him to get such an equation that just similar to the original one, so that he could get the relation of the Foci formula, or the relationship between the foci point and the distance of the two line, or the two segments, let's say, right in here, D1 and D2. I guess for you, since you have already know how to get that foci points by using this formula, the square root of a squared plus b squared, so you don't have to do that calculation by yourself again. If you can remember it, remember it's the last thing that you want to do in the learning. The best way is to learn stuff based on your previous experience or those knowledge that you have learned before. That's the best way to do, or the best way to go, because that will save you a lot of energy. Hyperbola is not centered at the origin. So this is the last video that we could learn. So let's get into it.
Let's see if we can tackle a slightly more difficult hyperbola graphing problem. So let's say I have the hyperbola, make this up on the fly, x minus 1 squared over 16 minus y plus 1 squared over, let's say, 4 is equal to 1. So the first thing to recognize is that this is a hyperbola, and we'll, in a few videos, do a bunch of problems where the first point is just to identify what type of conic section we have, and then the second step is to actually graph the conic section. So here, I already told you that we're going to be doing a hyperbola problem, so you know it's a hyperbola, but the way to recognize that is you have this minus of the y squared term, and then we actually have it shifted, right? The classic or the standard non-shifted form of a hyperbola, or a hyperbola centered at 0, would look something like this, especially if it has, I guess, the same asymptotes, just shifted but centered at 0. It would look like this: x squared over 16 minus y squared over 4 is equal to 1. And the difference between this hyperbola and this hyperbola, the center of this hyperbola is at, let's see, the center is at the point x is equal to 1, y is equal to minus 1. And the way to think about it is x equals 1 makes this whole term 0, and so that's why it's the center. And y equal to minus 1 makes this whole term 0. And on here, of course, the center is the origin. Center is 0, 0. So the easy way to graph this is to really graph this one, but you shift it so you use the center being 1 minus 1 instead of the center being 0, 0. So let's do that. So let's figure out more about, let's figure out the slope of the two asymptotes here, and then we can shift those two slopes so that it's appropriate for this hyperbola right here. So if we go with this one, let's just solve for y. That's what I always like to do whenever I'm graphing a hyperbola. So we get, let's see, minus y squared over 4, subtracting x squared over 16 from both sides, minus x squared over 16 plus 1. I'm working on this hyperbola right here, not this one, and then I'm just going to shift it later. And then let's say multiply both sides by minus 4, and you get y squared is equal to, see, the minus cancels out with that, and then 4 over 16 is x squared over 4 minus 4. And so y is equal to plus or minus square root of x squared over 4 minus 4. And to figure out the asymptotes, you just have to think about, well, what happens as x approaches positive or negative infinity? As x gets really positive or x gets really negative? And we've done this a bunch of times already. And I think this is important. This is more important than just memorizing the formula, because it gives you an intuition of where those equations for the lines of the asymptote actually come from. Because these are what this graph or this equation or this function approaches as x approaches positive or negative infinity. So as x approaches x approaches positive or negative infinity, as x approaches positive and negative infinity, what is y approximately equal to in this case? Well, once again, this term is going to dominate. This is just a 4 right here. You can imagine when x is like a trillion or a negative trillion, this is going to be a huge number. And this is going to be just like, you can almost view it like round off error. You take the square root of that. And so this is going to dominate. So as you approach positive or negative infinity, y is going to be approximately equal to the square root, the positive and negative square root of x squared over 4, so y would be approximately equal to positive or negative, what's the square root of this? X over 2, or 1/2 x. So let's do that. So let's draw our asymptotes. And remember, these are the asymptotes for this situation. But now, of course, we're centered at 1, -1. So I'm going to draw two lines with these slopes, with positive 1/2 and negative 1/2 slopes, but they're going to be centered at this point. Because I just got rid of the shift just so I could figure out the asymptotes. But of course, this is the real thing that we're trying to graph. So let me do that. Let's see, so this is my x-axis, my y-axis, sorry. This is my x-axis. And the center of this is at 1, -1. 1, -1. So x is equal to 1, y is equal to -1. Fair enough. And then the slopes of the asymptotes were positive and negative 1/2, right? Positive and negative 1/2. So let's do the positive 1/2. So that means for every 2 you run over, so if you go positive in the positive x direction 2, you move up 1. So you go to the right 2 and up 1. So that's the first one. And let me draw that asymptote. Yeah, it looks something like that. And then let me draw it from this point to that point. Oh, gotta have a steady hand. Okay, there you go.
Right, here he just said a word called asymptote. This word, asymptote. What is this? This is a line that normally you would say in the graph of a function. What it represented is a line that a function's value will try to approach but will never get there. If I want to use Chinese to explain that, that would be 渐近线.
Draw that asymptote. Yeah, it looks something like that. And then let me draw it from this point to that point. Oh, gotta have a steady hand. Okay, there you go. I think you get the point. And then the other asymptote is going to have a -1/2 slope. So remember, this is our center, 1 -1. So if I go down 1 and over, so when I go over 2, I go down 1. So that'll be right there. Let me draw those asymptotes, or that asymptote. It's going to look like that. And then just to continue it in the other direction, it's going to look, well, I want to make it, the lines overlap. It's going to look something like that. So we've drawn our asymptotes for this function, and now we have to figure out if it's going to be a kind of a vertical hyperbola or a horizontal hyperbola. And the easy way to think about it is to try to make, and we could do it two ways. I mean, if you just look at this equation right here, when you're taking the positive square root, we're always going to be slightly below the asymptote, right? The asymptote is this thing, but we're always going to be slightly below it. So that tells us that we're always going to be slightly below the asymptote on the positive square root. And we're always going to be slightly above the asymptote on the negative square root, because it's going to be a little less and it's negative. But I'll let you think about that. So I already tell you, my intuition is going to be there and there. It's more than intuition. I know that we're going to be a little bit less than the negative square root. But I'll do it the other way. I'll do it the way I did in the last video. So the other way to think about it is, what happens when this term is 0? For this term to be 0, x has to be equal to 1. And does that ever happen? Can x be equal to 1? If x is equal to 1 here, this term is 0. And then you have a situation where, let's see, if x is equal to 1, this is 0. And then you have a minus y squared over 4 would have to equal 1. Or this would have to be a negative number. So x could not be equal to 1. So y could be equal to -1. Let's try that out. If y is equal to -1, let's try out that point. If y is equal to -1, this term right here disappears, right? When y is equal to -1.
Okay, let's say, to be honest, since what this video does is try to tell you how can you graph a, how do they call it, how can you graph a hyperbola. Well, how can you graph a hyperbola which the center or the original point does not in the original point of your line. So it is simple. As long as you know that it is a hyperbola, then what you could do is to first find out the center point of that, then find the two lines that the graph will approach but will never get there. After that, you try out a few points. Then you could just try out a few XY pairs. You draw those points, then you connect those points together so that you could form a complete graph. It's something like this. Okay, I guess this is today's video, and inside of this video we have learned about all those concepts about the connect. Basically just let's say 1, 2, 3, 3 shapes or 3 graphs: the circle, the ellipse, and the hyperbola. We have noted the graph and its corresponding equation representation, and also how do they call it, the foci points of that. Okay, that's it. I will see you guys in the next video. Bye.